Good morning, everybody.
Good morning.
I hope that you can find it room in your heart to forgive me for the announcement spam that took place yesterday. You got to see me melt down
In real time.
over the chapter, whatever that stupid chapter is, homework assignment. I still have not taken the time to figure out what went wrong, nor am I going to do so. I don't care anymore. But the problems I assigned you that I picked out of the book back in December when I was doing this did not have any parallel problems in them. And all of a sudden, parallel problems were cropping up in this homework assignment. So I did several things, right? I removed one completely. And then I realized there was another parallel one, so I just gave you the answer, basically how to do it, right? And then it's sort of a final straw, and I don't know if you've noticed this yet, I just made that entire homework extra credit. Okay? So for those of you that do the homework, you'll get 1.3% extra credit to your grade. Because that's basically what a homework assignment is, it's 1.3% of your grade. So that won't look like it's being calculated correctly in Canvas until like all categories are filled in and the quiz doesn't get filled into the end. So if you're doing like the predict my grade feature, if you put the quiz score in, it should, like your score should jump a lot. It'll be the extra credit plus the, anyway. I got your back. I'll check at the end of the semester just to double make sure, but I ran a couple of simulations on live real-time grades. If any of you got announcements from the Canvas that grades were changing, that's what I was doing. Just to make sure that the extra credit was being applied correctly. It appeared to be doing that. So that entire assignment is now extra credit. For the people that did the old problem number 4, I'll go in and make sure you get extra credit, because that one's horrible enough. And if you really want to know how to do those problems, I guess you'll find out tomorrow. But don't, because that's due tonight, right?
Yeah.
Don't worry about knowing how to do those homework problems, except for the first question and the last question. Is there 5 questions now?
Yeah.
I think it's question number 5 was actually somewhat decent, if I remember correctly. Okay, in terms of the things I was trying to do. We have an AC RLC series circuit problem, first one on the list, right? Okay, comes out of this chapter. It is, if you study the 3 problems we did in class together, you'll be fine. I modeled the problems after those examples that I did, right? When I should have looked at the homework and modeled it after that and realized that there was a dumpster fire before you guys started. So that was my fault. And I do apologize, and I hope that I made it up to you by making it extra credit and all that kind of stuff. Any comments, questions, concern, complaints, or pushback for any of that? Okay, I didn't want to like just totally get rid of it and nullify hard work and tears and go tutorials. A couple of them, the go tutorials just tell you what to do, I think, at the end, right? So if you want to spend some time on that, do so, but I would rather you spend some time studying other things. If you need time later to go back and you want the extra credit, let me know, and I'll just go in and make it so that you can do it. But yeah, that's what's happening with that assignment. All right. Now that I'm a failure as a teacher, what are your questions? Let me guess. Right-hand rules. Right? Okay. So let me show you the Balogh patented method for remembering the right-hand rules. Okay? And maybe this is something I should have showed you right away in class, but I've done that before and it goes right over the heads of students. Okay? You need some time with the right-hand rule before I kind of show you the organization that I've got here. And again, this works for my brain. It may not work for yours. So I just, with that caveat in place, this is how I think of the right-hand rules, okay? there are two broad categories, and I think of just two right-hand rules, okay? There is a right-hand rule that is involved when you're finding forces. And then there are right-hand rules when you are finding magnetic fields, okay? And we called this one, I think, didn't we call it pew-pew? Okay? And it's the right-hand rule where you're holding your fingers, right? Like the pew-pew phaser gun type thing, right? Okay? And you got your three fingers, right? And what is your index finger? It's either velocity or current, right? It takes the direction of the velocity or the current. And then what's your middle finger? That's the magnetic field direction, okay? And then your thumb, that's the force, okay? And that's consistent, there's no variations of that, that's just what it is. And variations on a theme would be like, maybe you're not given the velocity, maybe you're given the field and the force and you're asked to find the velocity, right? So, but holding your hand in that shape and lining those things up, okay, will get you where you need to go. So there's the pew-pew, which always involves a force. If forces are being asked to find direction of force, being given a force, a charge in a magnetic field, you're doing pew-pew, okay? Then the magnetic field one, I do kind of divide into two different categories. Both of these are the hitchhiker. I don't know how to spell hitchhiker. Okay? Hitchhiker. And by hitchhiker, I mean you're holding your hand in a different shape, aren't you? Fingers curled into your palm, thumb pointed straight up. It's just, there's two variants of this, right? There's what I think of as the straight wire, and then the loop of wire, okay? So in the straight wire variation, what do you do with your thumb? It's the current. You let your fingers or your thumb be the wire, okay? So in the straight wire, your thumb is the direction of the current in the wire, and your curled fingers are then what? The magnetic field. And when we're talking about a loop of wire, your curled fingers go in the direction of the current, and then the thumb is the magnetic field at the center of the loop. So, you know, there was a picture, right? Something like this, where the magnetic fields are going around the wire, right, in sort of 3 dimensions. And then if there's a picture for this one, it would be a loop of wire with current flowing around it, and then magnetic field pointed out for that direction, right, clockwise. Or sorry, counterclockwise, it would point out of the screen. So what you're doing with this hitchhiker rule, right, it's a current and a field, which can be confused with pew-pew, right? Because current and field can end up in pew-pew, but pew-pew always ends with a force, or has force involved. If we're looking for the field of a straight wire, thumb is the current, fingers are telling me how I wrap around, you know, what direction the field goes around the wire. And then if we're talking about a loop of wire, my fingers go in the direction of the current, and my thumb is at the center. Now, of course, when we're using Lenz's law, we can invert these things. Like we can go at them backwards, right? So with Lenz's law, we point our thumb in the direction of the induced field, and our fingers tell us, because again, it's a loop of wire, right? So we do the field in the center, and our fingers tell us the direction of the current. Do something similar, like if I say that there's a wire right here, and field is pointed into below the wire and pointed out of above the wire, what direction is the current in this wire? Okay, so which of the hitchhikers are we going to use for this one? The straight wire one, right? Because we got a straight loop of wire, and this picture is trying to indicate a field that comes out and circles back in, right? So if I want to find the direction of current here, I've got to get my hands so that my fingers come out on top and wrap around and go back in on the bottom, and my thumb ends up pointing which way? To the right. So all of these right hand rules you can do forwards and backwards, right? It's just the straight wire one, your thumb is always the current. For a loop of wire, your fingers are the current. It may not be the thing that you're starting with. You can do it in reverse. But this is how I categorized them when I was studying them for the first time, and it's always stuck with me. This is what went on my cheat sheet, right? I wasn't allowed a cheat sheet in that class, but I put it down anyway, and then tried to get that memorized, and I ran right into the exam and flipped it to a blank page and just made this chart so that as I was going along and I was confused about where I was and sitting there going, because that's easier than thinking about physics, right? I was able to look at this and go, oh yeah, okay, fingers, thumb, whatever. And then after that, it's just lots of practice. It really is over and over again, making sure that you've got it right. I hope that helps. Right? I hope that helps you sort of summarize or put together. These are the kinds of things that you want to be doing, right, before you take an exam. You want to be summarizing information that's gone over in a unit or whatever is happening in class, specifically for STEM classes, right? We give you a lot of information, usually on a 3 to 4 week unit period, and then we test you on that information, right? Being able to pull together a summary of everything could help go a long way to your studies. All right, other questions? Things that you want to see done, need help with? You've given up already?
What exactly was the first question? Since I missed it. Was it just
Nobody asked a question. I just started summarizing the right-hand rules for people.
Okay. Did we need eddy currents at all?
I mean, the eddy current is what's being made in Lenz's law. That circulation of current that goes around. But specifically in terms of like magnetic braking and all that, no. Yeah, I think, what's the, that screen? So circular motion of charged particles in magnetic field is not an eddy current. Faraday's law up there, I'm giving you a calculation to do. Right? It would have said conceptual if it was like right-hand rule kind of stuff. But Lenz's, I originally wrote down Lenz's law and didn't put conceptual on it because Lenz's law is conceptual. And then I was like, oh yeah, no, I better call out that this is in fact a conceptual question, right? Now, can you safely navigate circular motion of charged particle and magnetic field without the concept behind it? No, right? But you will be calculating something, right? Magnetic field of a current carrying wire. Do you think a right-hand rule might be involved there? Right? Okay. And then I called out a conceptual question. So again, magnetic field of current carrying wire, I'm asking you to find the magnetic field of a wire, right? Distance from it, something like that. We had wires together, ABC, points ABC, all that kind of stuff. You're going to need right-hand rule to get through it, but there is a calculation. You're going to come up with a numerical answer. But the right-hand rule force on a moving charge, conceptual, what do you think you're going to be doing? You're going to be doing a right-hand rule. I give you some charges or a charge, and there's magnetic field, and you tell me the force or tell me the whatever, right? So it's a picture, and you're going to be applying the right-hand rule. And how do you explain which answer is the correct answer? By right-hand rule. I use the right-hand rule. And if it's wrong, it's wrong. If it's right, it's right. There's really kind of no way to give partial credit there, right? How do you know if the problem on the exam is conceptual? It's going to have multiple choice answer, right? That's me communicating to you, this is answering ideas. You can use math if you want. And then transformer, the answer is always Optimus Prime. No, don't, if you put down Optimus Prime, you will get -200.
Wow.
Half credit, a tenth of a point. I'll give you a tenth of a
Yeah, it's probably the
Everybody likes Bumblebee, and I don't understand why.
So it's seven questions.
Right, is there 7 topics up there, right? Yes.
For the ACRLC
Mhm.
circuits, are those questions gonna be as difficult as they are on the homework?
Now we know when you came into class. That homework is now extra credit for all of you that showed up late.
There was a train.
It went really bad. Yeah, there was a train wreck. And you guys got stopped by the train. Train wreck was me, you got stopped by the real train. Chapter 23 is now extra credit. The whole chapter, the whole assignment is extra credit. And basically, instead of just saying it's gonna replace, I could have done like replaces your lowest score on the homework or something like that. No, I'm giving 1.3% credit to your overall grade. Because that's what a homework assignment is equal to. And then, so you don't have to worry about it. The question on the exam that's listed up there is like the ones we did in class together. I did 3 examples. That's what you should study, not the homework. Because something went very wrong with the homework. I told you guys there would be no parallel, and then there were like, what, 3 questions that had parallel? Before I like pulled one of them for being, anyway. Yeah, the whole assignment. 1 and 5 are decent. But the rest were just stupid. And again, if you feel like, oh gosh, I can get extra credit, I better do all that work instead of studying for study for the exam, right? If you want another chance at the extra credit, just email me and I'll say you can do extra credit. In fact, do that after the key gets posted, and then your extra credit will be even easier. Other questions? Just a bunch of hardened physics students out there. I've already given up. Don't know what to ask. It's gonna be a right-hand rule, this way, yeah.
So, just look at the magnetic field of a current carrying wire.
What about what is it? How do you do it? That kind of stuff?
I mean, I just want to see it.
Just want to see it again?
Yeah.
Did you have a homework problem where there was like a vertical wire and a horizontal wire? And you had to find the magnetic field at a point? Am I remembering?
This is chapter 22.
No, yeah, that's chapter, sure, 22. 21? 22 is Faraday's law, 21 was magnetic field. Number 11, and it looked a little bit like, did it have like a wire like this and a wire like this, and you were finding the field like down there? And maybe there was like another point over here or something like that, yeah, that kind of problem. I did the problem, where there were 2 wires and then I was like at the different points, right? We could do like, this is particularly awful and I wouldn't do this to you, but like find the magnetic field at the point of that triangle. From all those current carrying wires. Yeah, don't think about that. But in all these cases, oh, check me, is the equation mu naught I over 2 pi r? Yeah? Yeah. So what's the r? Yeah, you always want to think of it that it's being radius, but it's not really. I mean, it is and it isn't. It's not the radius of the wire, right? What is it? It's the distance, the perpendicular distance from the wire, right? So if I wanted to find the magnetic field right here, it would be the sum of the magnetic fields from the 2 wires. I'd need this distance and I need this distance. So is this helping you at all to remember what's going on? Okay. In the case of two wires crossed like this with current going that way and current going this way, at that point, below the horizontal wire and to the right of the vertical wire, would I be adding those two fields together, subtracting those two fields? How do I know what to do with those two vectors? I mean, I can calculate the magnitude, but how do I know if the field is positive or negative? You gotta do a right-hand rule, right? So, which right-hand rule are we gonna do? Our force is here. No, there's no forces here, right? So this is a hitchhiker, isn't it? And which are the two hitchhikers? The straight one, because we got straight wires. Okay, so I do the horizontal wire, current to the left. My fingers are pointing into the screen above and out of the screen below. So I know B1 is out. And what about the magnetic field for wire number 2? Thumb points down, fingers go in on the left-hand side, wrap around to coming out. So what am I going to do to those two fields? Since they're in the same direction, I'm going to add them together to get the magnitude. If they were opposite directions, what would I do? Subtract. Usually, we say out of the page is positive. And by usually, that typically means if you have positive x to the right and positive y, that way your positive z, the third dimension, is out of the screen. And how do we know that? It's a right-hand rule. X, y, z. That's why the Cartesian coordinate system is called a right-handed coordinate system. Have you ever heard that in math classes? Yeah, it's because of a right-hand rule. X, Y, Z. And yes, there are left-handed coordinate systems. They're weird. They usually involve inverted space. I was in a class called condensed matter. It's like the second or third class of the semester, and the teacher's introducing us to inverted coordinate systems. Like literally your x-axis is 1 over x, and your y-axis is 1 over y and 1 over z. Apparently it was easier to talk about molecules in inverted space. Class never made any sense to me after that point because I was a dyslexic person sitting in a class talking about inverted space. Did I know where I was anymore? I hung on for the ride in that class. I literally just hung on. Did I ever use condensed matter in my career? There were some chemists in there that were really excited. Can I answer your question on that? Got to figure out the direction the magnetic field is pointing at that point, right?
Balogh, can you do an example of the, what's this law, like the decrease?
Yeah, you give me a problem.
Oh, God. Okay, hang on.
Give me a situation.
Remember if there was an example.
Okay, so coil. I'll start you. There's a coil of wire in the plane of the screen. North or south end of a magnet going towards it. North. Okay, towards or away.
Towards.
Okay, so north end of a magnet's going to head towards the screen. Okay, so increasing or decreasing magnetic flux through the coil? Increasing. Okay? Since the north end of my magnet's closest to this coil, which way will the magnetic field be pointing? It comes out of my magnet's front and pierces the screen, pointing into the screen, doesn't it? So it's increasing into. I now know that Lenz's law is going to increase out. And how do I know it increases out? It fights the change. And we came up with that table, didn't we? Of sort of all the thing, you know, Lenz's law always starts with the word increasing. Okay? All right? And now that I know it increases out, I apply which right-hand rule? Pew pew or hitchhiker? It's a hitchhiker rule. It's a coil of wire, so I know my fingers will be the current. But what do I know? What does that out tell me? The direction of the magnetic field produced by the coil, right? So I take my finger, I hold it in the direction out of the screen, and which way are my fingers wrapping around? Counterclockwise.
And the reason that the field is coming out of the screen is because the magnet was going in and it.
The reason the field is pointing out of the screen is because the coil will always fight the change in magnetic flux. Don't try to assign this some absolutes about, you know, you've got to identify these two things.
Yes.
And after that, the algorithm is very specific.
Okay.
Right? But it's the initial discovery of whether it's getting bigger or smaller and what direction that's happening that matters.
How do we turn that north and south
Well, I'm not sure I understand your question. North end of a magnet is where the magnetic field comes out, right? And south is where the magnetic field comes in. I'm not drawing all the loops there, right? But there's a direction to a magnetic field. Even though they form closed loops, there's a directionality, right? And as my north end gets closer to that part of the screen, right, the magnetic field lines are, think of it like water erupting from the end of a hose, right? The water's going to hit the screen trying to go this way. So that's how I knew it was into.
Let us know in the problem, which is.
No, I'll let you go. No, yeah, I mean, I've tried to make it clear. And if it's not clear to you, what do you do? Suffer in silence. Just ask, right? And I might tell you, well, everything's there, I'm sorry. My 2A students, boy, this last test, they were like, Mr. Balogh, how do I do physics? Yeah, you were there. Those of you who are here early listening to the lecture, would you rather do that stuff? The right-hand rule? No?
That was the second.
What are they learning?
Yeah, that was the second, they just took their second. And we started momentum today. You read the momentum. Let's see, more of these Lenz's law-ish type problems. Here's a coil of wire. Am I turning a magnetic field on or off? Yeah, you give me whether this field is turning on or off. On. Okay, so there's a coil of wire that doesn't have any field in it, and I suddenly turn on a magnetic field, right? And what direction is the field pointing, in or out? Out. So I am generating field inside of this coil. All right, increasing or decreasing? It's increasing because I turned it on, right? It went from 0 to something else. Which direction? Out. So what does Lenz's law say? Increase into, which way do I hold my thumb? Into the screen. Which way does current go around this coil? Clockwise. A
That was helpful.
what?
That was helpful.
Well, let's do more.
Yes.
Please torture me, Mr. Balogh, with more of these.
Yes.
Okay,
Keep going.
on Thursday I will. This is gonna be hard to draw. That's supposed to be a coil of wire in 3 dimensions. I'm not sure I pulled it off, but yeah, let me draw it this way. That's a coil of wire. The plane of this coil of wire is perpendicular to the page. So in other words, there's like the wires coming out and going back in at the bottom, right? It's circulating around, okay? And there is a magnetic field directed like that through the center of this coil of wire. And I turn that magnetic field off. Which way is the current flowing in the wire? In other words, what direction is the current at the top of the loop versus the bottom of the loop? So, we start with increasing or decreasing, right? Turning the field off, what's happening? We got a decrease. What direction?
We're looking at the top one.
You're looking at the magnetic field. What direction is the magnetic field pointing?
Right.
To the right. Oh, Mr. Balogh, this isn't into or out of. What do I do? Let's go with it. A decrease right would be met with, again, we always have to be increase.
Increase left.
Right.
Oh, yeah.
Right, because if it's in or out, if you switch it to in or out, then it's
It's the same. It's the same. It's the same. It's just different words.
it's hard, I know.
It's getting weaker pointed to the right. What does the coil want to do? Keep it to the right. It wants to it fights the change. Not the direction, it fights the change. Direction's important, but it's the change that's more important. So it increases right. So what direction do we put our thumb? To the right. Okay. My thumb's to the right. The induced field is to the right. What direction is the current at the top of this coil? It's out. And what's the direction of the current in the bottom? In. So that would be in, that would be out. It's the same picture as this. That's the picture rotated like 90 degrees, where now the magnetic field is coming out at us, right? And if it decreases out, then my thumb is out and it will go around counterclockwise, which is consistent with that direction. How do you change flux? What is flux? It's magnetic field, its area, and its orientation of area with respect to that magnetic field. So to change the flux, what are the 3 things that can change? The magnetic field, the area, and the angle. I won't give you anything like this on the exam, but how would you change the area? A coil of wire shaped like a diamond is in a magnetic field pointed out of the screen. The two corners of the diamond are pulled, and the coil collapses. Right? If I were to pull that, the two tops would come together, right? Okay? That's an example of a change in area. Okay? So here, is the flux increasing or decreasing? It decreased. Why did it decrease? Because the area got smaller. What direction was the magnetic field pointed? Out. So it decreased out. So what's the coil going to do? Increase out and get a counterclockwise flow. Changes in angle are always about a coil rotating. Okay. So again, just look at the change in flux, increasing or decreasing, and then what direction. I'll admit to you, it's kind of scary, right? It feels like you've got a 50-50 chance, doesn't it? Like, and maybe not a 50, maybe a 1 in 4, because it's 50% times 50% or something, right? Okay. But if you can nail that, what the flux is doing, and the direction, everything else is quote unquote automatic. In that you know what Lenz's law is going to say, then you know you've got to get your thumb in that direction. Ashton, did I answer your question sufficiently?
Yes, you did, thank you.
Guys ready? Should I just go get the exam? You don't need that much time on it, right?
Please.
Open note,
What?
is it open note today?
Oh, you do not want an open note exam. I promise. I used to do those.
How will we
Were they hard?
Oh, were they hard?
No, I didn't say were they hard, were they harder than our exams? Okay. That's what I figured.
Because you have access to all the information.
Yeah.
So go for the jugular.
That's terrible.
No, I mean, I very much designed the exam knowing that you would have one 8.5 by 11 sheet of paper with which to put the sum total of your brain onto. The thing that would happen most often with open notes is that a student would come in and open the exam and then open the book and start like reading for the first time.
Oh,
Have I told you that I did 2 master's theses? No, okay. One of my master's theses was in extreme ultraviolet lithography. Talk about that later. It's in the optics section. My other one, the one that was near and dear to my heart, was how physics students learn physics. And we studied, in particular, there was this brand new thing called the internet. And we studied how the internet was affecting education and what online classes might look like in physics. So like I was there when the internet was born. And the thing that we saw, especially with like online quizzes, is that students were easily taking 10 times longer to do an online quiz versus a quiz in class. And when we looked in and we studied what was going on, students in the online classes were waiting for the thing to be, because there was no way to do a time limit at that point. So it's just like you gave the question and then, but we could time how long they were on the screen, right? And so we got all this data, and when we asked them post follow-up questions and case studies and stuff like that, focus groups, they told us, oh yeah, I just opened my book I didn't bother to study, I just opened my book then, looked at the question, looked at what I had to do, studied it in that time, and then answered the question. Okay, yeah, and that works, but it takes a lot longer. Oh, by the way, there's very little difference between a class of 300 students learning physics and taking the class online. Students feel just as isolated, just as alone, and do just as bad. So what do? Don't teach classes with 300 students.
Didn't you say you taught a class in the forum hall?
Not here at this campus.
Oh, okay.
I taught classes at BYU in their forum hall
Oh,
that held anywhere from 200 to 800 students.
goodness.
The largest I ever had was 300. And that was physical science. Just a bunch of English majors not knowing how to do science.
Yeah.
Yeah,
Can you do an example of transformers?
Transformers? Sure. Help me out. Do you want the one that brings power to your house or that charges your phone? Charges your phone, okay. Most phones charge on the USB standard of 5 volts. So USB-C, USB-A, the standard is that you don't exceed 5 volts across that connection. However, the power can be vastly different. How many of you have heard of like quick charge or any of that kind of stuff, right? Okay, so the little tiny bricks, okay, those usually are a 5-watt charger. And then if your brick is a little bit bigger, that could be a 10-watt. And I believe the current generation of iPhone with the USB-C, I think it can do 45 watts maximum. Android has a 60-watt standard. And then things like laptops and iPads and all that kind of stuff, they can go up to like 300 watts over a USB-C connector. I think the USB-A, the standard USB connector, I think that one's only good for 40 watts, 60 watts. There's some limitation to that one. Anyway, all of this power, right? If all of these things are at 5 volts, then what's different? It's the current, isn't it? Okay? It's the current that's different. So power being current times voltage, right? If you set it 5 volts, the only way to get more power is to get more current, isn't there? So we need to take the 120 volts at the wall and bring it down to 5 volts, don't we? So let's figure out what it would take, right, to get a step-down transformer to do this, right? So we know that the voltage in the primary, no. Yep, I'm doing this from memory. Is this correct? Voltage in the primary divided by number of turns in the primary is equal to voltage in the secondary divided by number of turns in the secondary? Yes? I don't have my cheat sheet. No?
Yeah.
Yeah?
Yeah.
Okay. So, voltage in my secondary, I know it's 5 volts. So what happens if I shove some stuff in here? So I know my primary is 120. I know my secondary is 5. But I have like 2 unknown things here, right? So what I can solve for is the ratio of turns. I can do N2 over N1, which would be 5 over 120. Basically, I move the N2 up here, and I take the 120 and I move it down there. You can say I multiply or divide both sides by 120 and multiply both sides by N2. Whatever floats your boat. But here I'm getting a ratio of turns, right? what's 5 divided by 120? .042. So that's just a number. That's the ratio of turns, right, that I need in order to step down from 120 volts to 5 volts. So what does that mean? I can't put one turn in my primary, okay? Because then I would only have 0.04 turns in my secondary. Usually you need at least a few turns in your secondary for this to work. So I want to make sure that, like, if I know that I want my secondary to have 100 turns in it, how many turns does my primary have to have? Well, if N2 is equal to 100, right? Then that means N1 is going to be equal to N2 divided by 0.042, which is 100 divided by 0.042. Nope, other way, Mr. Bill. 2, which means I need 2,381 turns in my primary. That's a lot of wire, isn't it? So I could then keep designing and say, okay, well, I don't want 100 turns in my secondary, maybe only 10 turns or something, right? You can start playing around with this to get the voltage to be what it, to go from 120 to 5.
Would a question, in a problem, ask how many turns that is?
Yeah. How many turns would it take, or what's the ratio of turns, or what's the voltage in the secondary if the ratio of turns is blah, blah, blah. Like, you don't always have to know exactly what the turns are. You just need to know that if you've got twice the number of turns in the primary as the secondary, well, first of all, is it a step up or step down transformer? If the primary has twice as many turns as the secondary, which way are we going here? Down. A step down transformer, okay, means that you go from a bigger number of turns to a smaller number of turns. A bigger voltage to a smaller voltage. Right? And then, it's the ratio. Usually transformers, they don't tell you how many turns are in, they tell you the nature of the ratio. Because it's the ratio that just tells you what the voltage ratio is. Yeah. Where was I going? Oh, current. So what happens to the current though? If the current's going down, if we're going from 120 to 5 with the current, or the voltage, what happens to the current? It goes up, right? So we can increase the current by going down in voltage, which is why you go from the household voltage of 120 down to 5 volts for computers and everything else. Most computers run on a 5-volt rail. There's 12 and 24 volt systems in computers. A lot of laptops have gotten rid of some of those higher voltage, just again to get more current. More current, by the way, equals more heat. So if you've ever felt your laptop or your iPad or anything get hot, it's actually ramped up the CPU and the memory and everything to do whatever it is you're asking it to do, and it's generating more heat. That power gets dissipated as heat. Light and all the other things in your device. Yes, the ability to charge your phone, brought to you by Michael Faraday and Faraday's law of electromagnetic induction. Because without it, transformers wouldn't happen. Everybody knows that Edison was a jerk, right? Did we? Or he treated his employees badly and said that he invented a light bulb, when in fact he never invented a light bulb. He just invented 1,000 ways not to make a light bulb and finally just had enough money to get the right answer. Thomas Edison was in a battle with Nikola Tesla over what kind of electricity would be delivered to homes at the time that electrical grids were coming online. Edison was a diehard fanatic of DC. He thought DC was the future. He couldn't have been more wrong. Because with DC, you can't play these shenanigans with switching up and down. And Tesla knew it. Tesla knew that you could trade current for voltage and keep the energy the same. And it was Teslas that won out because of physics. Like, simply. Edison went on to be some household name and inventor, blah, 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 and famous. Nikola Tesla ended up dirt poor, dying of mental disorder in an apartment in Chicago, right? It's just a sad story about what happened to Nikola Tesla and what happens when you let the robber barons run amok. Yeah, physics wins, always. I should say the universe. Physics is our understanding of how that works. Either give you more anecdotes from history or you can do basketball. I seriously want to teach a history of science class.
That would be cool.
Oh, it would be so much fun. All that stupid wars and art history, we just throw that aside and talk about how the human race has gotten better and better at understanding how the universe works. And consequently is getting better and better at destroying itself. Be a good class.
Can you go over a circular motion?
Yeah, circular motion in a magnetic field, so now we're talking, and I'm not gonna know the equations off the top of my head for this one. This is the cyclotron, the mass spectrometer. Thank you for reminding me of this, yes, I wanted to point out, right, I'm directly referencing that. Circular motion of the particle in a magnetic field, so, if we had a magnetic field pointed into the screen, right? And a particle is traveling in a straight line path and then, with the speed v like this, right? Which way is it gonna curve or bend or circulate? Now we're talking about forces. How do we know we're talking about forces? I've got a V, I've got a magnetic field, and I'm talking about pushing this thing into a circular path. And circular paths are always got a centripetal force, right? A force pointing towards the center. So here, I would do my V with pew pew. My index finger points to the right. My middle finger has to point into the screen. I can rotate around my index finger, right? Okay. And then what direction does my thumb point? It points up. So this particle would curve that way. Okay? If the field's strong enough and say it entered at the bottom, it can curve so much that it would just go into a circle, right? And circulate within that magnetic field. So how do we find the radius of that circular path? We can either reinvent the wheel, apply Newton's second law, and come up with it, or use the equation I gave you. I gave it to you in class. Do I have it right here for me? Where's my cheat sheet for that chapter? I have a cheat sheet for every chapter. I wrote down MV times QV. That was at least one of them I gave you. The book decided to solve for mass, doing it this way, where there's a voltage involved that's being applied. Okay, I would worry more about this than the book's way of doing it, because this more applies directly to a velocity selector type situation.
So we don't really need it.
So use the one that you scored.
It's more generally applicable.
And so the torque equation, we don't really.
No torque. If I wanted you to do torque, I would have told you. series circuits like the one we did in class, circular motion we just did, Faraday's law. Calculations involving Faraday's law. What are you doing? Change in flux, right? So you've got to be able to calculate the change in field or the change in area. Not the change in A, I wouldn't do change in A. Lenz's law, conceptual we covered. Right, we did that one, right? And focus on a moving charge. So I just did that again. And then transformer we did, right? Do we want to do more right-hand rules with forces on moving charges? A little bit of practice. Which way is the magnetic field pointing? Give me any direction. Left. Here's a magnetic field. Charge moving any direction. Up. What direction will the force be on this charge? B. Thumb points which way? Out. Give me a magnetic field direction. Down. Give me a force direction. What direction is the velocity of this particle? Let's see. I don't have an index finger, but I do know that the magnetic field has to point down, and my thumb has to point out of the screen. So which way is the velocity? Going to the left. Give me a magnetic field direction. Give me a, I don't care. You know what? What's that? Another hitchhiker? Okay, we'll get there in a second. Give me a velocity. Down. Give me a force. My B is down. My force is out of the screen, so which way is my middle finger point? To the right. Kamal, you said more hitchhikers? Just like finding the magnetic field of a wire, of a loop, like what? Wire, so wire or loop? Wire. Which way is the current flowing? Any direction. Up. Magnetic field on the, around this wire. My thumb goes straight up. Fingers are coming out on this side, going in on that side. Circulating around the wire. Loop or wire? Loop. Field or current? Current? Is the current clockwise or counterclockwise? Counterclockwise. The field of this loop points out. Got my hand around, and there is my field. Wire or loop? Loop. Current or field? Field, in or out? Current flows clockwise. How do I know? Where does my thumb go? In, and fingers wrap around. Wire or loop? Wire? What direction is the current? Or what direction is the magnetic field? So The magnetic field is pointed in. There, but it has to circulate. So that means somewhere else it has to point out. Right? So there must be a wire right here. What direction is the current in that wire? My fingers have to go in at the top, wrap around, and come out at the bottom. So which way is my thumb pointed? To the left. Give me a magnetic field circulation direction, clockwise or counterclockwise? Clockwise? So the magnetic field is going that direction. What direction is the current flowing from the wire that's making that field? Hitchhiker or pew-pew? It's a hitchhiker because there's no force here, right? I'm finding a field from a wire. Which of these is the straight thing?
Straight thing.
I got a curly thing and I got a straight thing. Straight wires make circulating fields, right? Circulating wires make straight fields. Is the field circulating or straight? Circulating. So I wrap my hand around in the direction of the field. Which way is my thumb pointed? In. That means my wire at the center of this field, the current is flowing into this screen. If this current had been flowing to the left, then my magnetic field would be out on the bottom, in on the top. It's like a rotation, like I take this picture and I just rotate it like that. Look at it from the side. You can do this in Discord. Program the bot to give you random direction. The current points left. The magnetic field points left. What happens if your field and your current point in the same direction? What direction is the force? Zero. You can't. Yeah, you have to. They have to be perpendicular, right? In some sense of the word. Yeah. You may label your fingers. I will not consider that cheating. I will consider that mild insanity, but yeah, you do you. Yeah, I'll be watching you very closely during the exam, not because I'm worried you're gonna cheat, but because I'm worried you're gonna lift up your left hand. You laugh. I watched it happen. Student, knows what they're doing, on top of it, stress of the moment. If her whisper in their ear, you just used your left hand, and they look at me like, hit.
I don't know why, this is a terrible idea. You need like one of those mini marshmallow launchers, just launch marshmallows and people use their left hand.
I need
In his hands, maybe not.
because I can make him go supersonic.
Yeah. Yes.
Yeah.
Yes.
I used to throw those little bits of chalk.
That's me.
Yeah, way worse.
Back in the day when we could abuse you.
Could or just
What?
Get caught.
Well, it was an earlier age, right? You weren't so enlightened back then. I had one of my fellow teachers admitted that he used to do that. And one time he picked up a piece of chalk and he threw it, and the chalk, the student he was trying to hit probably said something like W for a meg or something like that. That student ducked. So it's like, if I'm trying to hit that, right? That student ducked, saw it coming, and the piece of chalk came in, hit the very edge of the desk, and pulverized.
Yeah.
Right into the face of the student, covering them in chalk. I try not to turn green anymore. Hulk out. Although I have been exposed to gamma ray. Explains a lot, doesn't it? Any other questions? Yeah,
Like the force of that current in a magnetic field, this sign, the angles between magnetic field.
the angle between the current and the magnetic field, yeah. You're talking about ILB sine theta? Yeah. It's always the direction of the velocity slash current and the magnetic field. Have a good rest of the day. If you have more questions, come on up and ask me. But I will see you on Thursday for the moment you've all been waiting for.